Hi there, everybody. Today we're going to finish the last lecture section in the course, section 6.4. And what we're looking at here is difference in means, mu1 minus mu2. So let's jump right in. So this section is set up similarly to the other sections in chapter 6. First thing we do is look at the distribution of means, then confidence intervals, then hypothesis tests. So this is a distribution of a difference in means. Obviously, we've been doing this since chapter 2 or 3, really. But this is sort of, wrapping it all up. So the parameter of interest is the difference in the population means. The central limit theorem that we've talked about a bunch so far from chapter 5 says the distribution of the sample statistic, x bar 1 minus x bar 2, follows a normal distribution if the samples are large. And we're going to see what a large sample means here in this section in a bit. So for large N, the distribution of the differences in the sample means from populations with known means mu1 and mu2, so those have to be known, and the standard deviations have to be known, has this distribution. The distribution is normal, centered at mu1 minus mu2 with the variability given by the standard error. And when that happens, so we can use the standard error based on this formula. Now this formula looks really similar to the one from section 6.2. All we're doing is just tacking on another sigma squared over n inside the radical. And the idea here is we need both samples to be large or normally distributed, or one of each. So each sample has to satisfy the large sample condition individually. They don't both have to be large or both normally distributed. They just each have to have one of the two. And it turns out that in the formulas later on, we're going to see that if we don't know sigma 1 and sigma 2, then we're assuming we don't know mu1 and mu2 because you need mu to compute these. Then we replace these with the sample standard deviations in the standard error formula. So let's see how to use this formula. Again, this section is very similar to previous sections. Random samples of the given sizes are drawn from populations with the given means and standard deviations. Find the distribution of differences in sample means. So if we take samples of size 100 from population 1 with mean 87 and standard deviation 12, and samples of size 80 from population 2 with mean 81 and standard deviation 15, what is the distribution of the differences in the sample means? Well, we're just going to use this formula here, right? It's normally distributed, centered at the population parameter, variability given by the standard error. So there's our standard error. So the center of the distribution is mu1 minus mu2, right? So 87 minus 81. So our try that again. There we go. So distribution is centered at 6. Then we use the formula on the previous slide, and I'm going to build it the same way I've built all the formulas so far. Build a radical, build a fraction, build another fraction, and then just fill in the blanks, right? Because we want it to look like this. All right. So sigma 1 squared, so sigma 1 is 12 squared, right? Then we square it. And the samples are size 87, so we divide by 87. The second one, the standard deviation is 15, so we square that. And those samples are size 80. So I just identified all the pieces, right? You go through and you label mu1, sigma 1, n1, right? So I did that, and then I just plugged everything into the formula, right? Oh, sorry, I messed up. This should be a 100. I bet you some of you out there were catching that. and saying, oh man, he's about to mess up. There we go. Right, so just make sure that you type it in, exactly the way it looks here in the formula. And then just hit enter. And just round it to the number of decimal places stated in the homework. On a test, you'll be told how many decimal places to round. So the distribution of the differences in the sample means is distributed normally with a mean of 6 and a standard error of 2.062. So that's basically how it works. It's really similar to the stuff we did earlier in Chapter 6. The justification of where this comes from, that's way too mathematical for us to get into. But if you were to go into StatKey and build either a randomization distribution or bootstrap distribution, you'd get numbers really close to this. So that's the idea, that the stuff we did in chapters 3 and 4 supports these formulas, even if we don't prove that these formulas are correct. You will not have to know why these formulas work. You just read them off the formula sheet, type them in the calculator. For a single sample, we use n-1 degrees of freedom, but now we have two possibly different sample sizes. When we're performing inference on two sample means, the degrees of freedom value will be whichever is smaller, n1 minus 1 or n2 minus 1. So the df comes up when we use the t-distribution, just like we did in section 6.2. And in section 6.2, the df was just n minus 1. But here we have two different sample sizes. They could be the same, but most likely they're different. So we just choose n1 minus 1 or n2 minus 1. And so when we do a confidence interval, it's just centered at the sample statistic plus or minus z star times the standard error. But we can only use z when we know the mean and standard deviation, or we know the standard error. If we're computing the standard error based on statistics from the sample, we have to use a t-distribution, and that's what it says at the bottom. So this is really set up just the same as section 6.2. The only difference is that you have to check two numbers for the degrees of freedom instead of just computing one number. So here's a confidence interval for mu1 minus mu2. Here's just a summary of everything. So we have to make sure the samples are large or normally distributed, or one of each. The standard error, you can see, uses a formula similar to the one we used in example 1, except these would be sample standard deviations instead of population standard deviations. The margin of error is everything to the right of the plus minus in the confidence interval. That has not changed since chapter 3. So I just labeled the margin of error separately. A lot of the homework problems ask for the margin of error. And the confidence interval is this big thing. So we're going to compute it in steps like we've done in the past. Going to break everything all the way down, because you never know what the homework's going to ask. You never know what you're going to have to do on a test. So make sure you can break all the steps down. Okay, so if our sample results are the ones given, I'm not going to read them out loud. We need to give the best estimate for mu1 minus mu2, margin of error, and 95% confidence interval. All right, the best estimate for mu is, hopefully you all said it out loud, it's x bar 1 minus x bar 2, so it's going to be 6.2. Right? Sample statistic is always the best estimate. That's the center of our confidence interval. Next up, margin of error. So in order to do the margin of error, we need t star and we need the standard error. Well, the standard error we compute using the formula. So let's go ahead and get t star. So let's look at what we have here. So t star, we need the degrees of freedom to use either StatKey or the graphing calculator. So we want the smaller of n1 minus 1 or n2 minus 1. Well, n2 minus 1 is smaller. So our degrees of freedom is 20 minus 1. It's 19. So when we do our inverse t, now you can do this in StatKey as well. I showed you in the last video how to do this in StatKey. I'm just going to use the calculator now. So inverse t, it's a 95% confidence interval, so I'm doing 0.975. Degrees of freedom, 20 minus 1, which is 19. Right? So you can use StatKey or a graphing calculator. It's good practice to be able to do both. If you forgot how to do it, go to the previous video. All that's explained there. I want to keep this video under 45 minutes, unlike a lot of the other ones. All right, so again, round it to the number of decimal places stated in the homework problem. Usually for intermediate calculations, you round these to either 2 or 3. Just like I said, follow the directions on the homework or on the test. Here I'm just keeping 3, just for the heck of it. Now, the standard error, we just plug in S1 and S2 here. So make sure that you can get this number. So go ahead, pause the video. You don't need the parentheses. I just put them in so it looks a little, maybe it looks a little nicer. So put this stuff in your calculator and make sure you can get this right now. And you might want to build it like this if you're not sure. Or you can do the intermediate calculations. You can type like just the inside the radical first and then go back and put a square root on it. So I put the intermediate calculations if you want to check your work as you go. Not everybody just likes typing things into their calculators, sort of blindly. All right, so there's our standard error and there's our t star. So the margin of error is just multiply them together, right? So t star times the standard error, and you get 5.641. Again, I'm still keeping 3 decimal places. For my final answer, maybe I want 2, so I want to keep a couple extra digits, at least 1 extra digit, for the intermediate calculations. And for the last part, we just compute the confidence interval. So it's the sample statistic, 6.2, plus or minus the margin of error. We already computed this on the previous slide. So 6.2 minus that is that. 6.2 plus that is that. Go ahead, pause the video, make sure you can get these numbers. And then we have to interpret the results in context. We're not given the full context here, but you still want to state it out loud. You know, we're 95% confident or 95% sure that the difference of the population means is between those two numbers. So if you can handle the formulas, this is pretty easy stuff. The hardest thing you're going to have to do on a test or on the adaptive practice is identify what type of problem it is. Is it a single mean? Is it a difference of means, single proportion, or difference in proportions? That's what gives most people the most trouble. All right, let's keep going. So now we're going to look at a hypothesis test. And this follows the same template that we saw in the previous section. That it's just when we have a normal randomization distribution from chapter 4, we can use this z statistic, which is just the sample statistic minus the null parameter over the standard error. But when we don't know the parameters, we have to replace our z statistic with a t statistic. So let's see how to do that. And our degrees of freedom is still the same, right? n1 minus 1 or n2 minus 1, whichever is smaller. So everything here is the same as what you've seen in previous sections. You saw this in chapter 5, and these are actually the same as what we just did a second ago. The large sample conditions are the same. The standard error formula is exactly the same. And we saw this in chapter 5. In chapter 5, we called it a z because we were given the standard error. Here, we're computing the standard error, so it's a t. And we're going to use the alternative hypothesis, the t-value, and tcdf on the calculator to find the p-value. Again, you can check all your answers in StatKey. That is all covered in previous sections. So use the t-distribution in the sample results to complete the test of the hypotheses. So we're going to use 5% significance. We're assuming random samples, and if the samples are small, we're assuming the distribution is normal. These samples are both large, so the underlying distribution doesn't matter, right? Both samples are above 30. And then we're going to test mu1 equals mu2 against mu1 not equal to mu2 using these sample results. So the idea here is we're going to do the whole test. So first two steps, follow the template that I outlined at the end of section 6.1. Sample statistic first, no matter what. Okay, so our sample statistic, so this is a difference in means, so our sample statistic is x bar 1 minus x bar 2. Right, so it's negative 5. Next up, compute the standard error. There we go. It wasn't working. I'm going to show you an alternative way to type this in if you want to see one. It's a little quicker. So you can go not that. You can do 8.2 squared, and then you can divide it by 30. Because PEMDAS works under the radical. As long as you type it all in under the radical, you don't have to build the fractions. Just wanted to show you another way to do it. So 6.9 squared divided by 40. Right? So negative 5 is our sample statistic. Standard error, 1.8525. I'm keeping 4 decimal places here because I have to divide by this number. So it's never a bad idea to keep a couple extra decimals for intermediate steps. Next up, the t-statistic is just x bar 1 minus x bar 2. We already computed that. That's negative 5. Divided by the standard error, 1.8525. And you get negative 2.7. Again, if, let's say, you rounded the standard error to 2 decimal places, this one comes out the same. It doesn't always, but you should always check. So, just to be safe, keep a couple extra decimals. All right, now we have our t-statistic, and it's a two-tailed test. So what am I going to type into the calculator? Well, you might want to draw the picture, right? It's almost the same picture, but I'll draw it again. Right, doesn't have to be perfect. Now our t-statistic is way over here. It's negative 2.7. It is really far to the left. And I'm going to be shading to the left. So this is going to be a TCDF. This is a two-tailed distribution, but I have to do the correct tail first and then double it. So negative whatever big number you choose. Negative 2.7. Oop. Degrees of freedom. So do you remember what the smaller sample size was? And then subtract 1. Right, so our degrees of freedom was 29. Type in everything exactly the way it looks. You get 0.0057. Again, I'm keeping a couple extra decimals here because I want to round it. I want to double it. So we have a two-tailed alternative hypothesis. So I just multiply by 2 and I get 0.011. And you can see StatKey gives us the same answer. And because this is a small p-value, this is statistically significant results, that gives us sufficient evidence to conclude the population means are not equal. And if you were given some sort of story going on behind the scenes, you would have to interpret that in the context of the story, as we've seen in the past. All right, so that's it for the section. I didn't go over a million examples. You have examples, extra examples here in the book that you can do. I outlined about 20 of them that you can go do. That can help. All these are odd problems. You have the worksheet on Canvas that has some worked out problems. Now, some of them are homework problems, some of them are from the book. And if you want to stick around at the end of this video right now, I'm going to show you how to do the calculator shortcut. But the calculator shortcut doesn't always work. So I just want to warn you that if you're not sure if you want to use the calculator shortcut, I'm going to show you what happens. Sometimes it works, sometimes it doesn't. So that's it. Moving on to show you the calculator shortcuts, which are also posted on Canvas. They have their own videos and stuff. But I just want to just show you how to do the problems here using the shortcuts. You don't have to do the shortcuts, so if you don't want to do it, just go ahead and log off now. And if you have questions, talk to me in class. For those of you sticking around for the shortcuts, here we go. Oh, wrong button. Oh, jeez. All right, so it's stat. This app is hard to read on my computer. So stat, and we're going to tests. Now, this is a 2-sample t, but it's a confidence interval. So you have to go through and look for 2-sample t interval. Right there, 2-sample t interval. We're typing in the statistics, so just type in everything the way it looks. 75.2, 10.7, 30, 69, 8.3, 20. Confidence level was 95%, so that stays the same. Pooled, we don't use pooled. Oh, keep going down and then hit calculate. So there's your confidence interval at the top. So you can see it's not the same. And the reason it's not the same is because of this degrees of freedom calculation, right? Look, oh, it doesn't show the degrees of freedom calculation on this one. It shows the degrees of freedom calculation for the hypothesis test. So this, if you use this on the homework, this is not going to be close enough, right? And what's going on here is that your graphing calculator with the shortcuts is using a different formula to compute the degrees of freedom. It is not using n1 minus 1 or n2 minus 1. It's using this very complicated procedure. So there's nothing we can do about that. So this still can be used to answer some questions. But if you're typing these numbers into StatKey, this is not going to be accurate enough. StatKey requires... I'm sorry, if you're typing it into the homework, it's built around StatKey, not these calculators. Now, if you're just trying to answer basic questions like, does a difference exist between the populations? Well, 0's not in this confidence interval, and it's not in this one, so they would give you the same answer in that sense. If you were using this confidence interval to reject a null hypothesis, for example. So you can use this to answer some questions, but not all. All right, let's look at example 3. So we're going stat test again. Now this is a 2-sample t-test. Again, we're putting the stats in. So 51, 8.2. Sample size happened to be the same. It's a nice coincidence. 56, 6.9, and 40. We have a not equal alternative. We are not pooling. And again, you can see that the p-value is different. Right? So we got a p-value doing this of 0.011. This is 0.009. If it's just asking about reject or do not reject, this is close enough. But if it's asking about the p-value, if it's rounded to 2 decimal places, it's the same. If it's rounded to 3, it's not the same. And again, you can see the DF value here is different, right? When we did the problem by hand, our DF was 29. The calculator lists it as 56. So there's nothing you can do about this. So that's just a word of caution that if you like these calculator shortcuts, just be cautious that you know how to do it the other way. Because on a test, this might be multiple choice. And if there's only one answer out there that's correct on a multiple choice, right? On a short answer, as long as you're showing your work, I'll accept work with this. So on a test, this is fine. But just understand that multiple choice, if your answer doesn't show up, you got to pick the closest answer. And for the adaptive practice, you just got to be careful too. Because there might be differing answers. And on the homework, it might give you different answers. So that's it for this video. It's been a fun course. I hope you learned something. And next thing you will do, if you haven't already done so, is watch the lab video. And then that'll be it for the semester. So if you have any questions, post on the discussion forum or ask in class. And see y'all in class. Bye-bye.